If you're into quantum physics, this is exactly what you need. So, what is a wave function? In simple terms, a wave function, often represented by the Greek letters, which in modern day we call lowercase and capital psi, is a mathematical description of the quantum state of an isolated quantum system. It's not just any number though. Wave functions are complex valued, meaning they can assign a complex number to each point in a region of space. Now, let's get into the Born rule. This rule allows us to turn these complex probability amplitudes into actual probabilities. Essentially, the squared modulus of a wave function gives us the probability density of measuring a particle at a specific location. And here's a key point. The integral of a wave function's squared modulus over all the degrees of freedom of the system must equal 1. This condition is called normalization. But remember, since the wave function is complex valued, we can only measure its relative phase and relative magnitude. To get measurable observables, you have to apply quantum operators to the wave function and calculate the statistical distributions. Wave functions aren't limited to just position. They can also be functions of other variables like momentum. You can convert a wave function dependent on position into one dependent on momentum using a Fourier transform. Some particles, like electrons and photons, have non-zero spin. The wave function for these particles includes spin as an intrinsic, discrete degree of freedom. For systems with internal degrees of freedom, the wave function at each point assigns a complex number for each possible value of these degrees of freedom. These are often displayed in a column matrix. According to the superposition principle of quantum mechanics, wave functions can be added together and multiplied by complex numbers to form new wave functions. This forms a Hilbert space where the inner product between two wave functions measures the overlap between the corresponding physical states. Lastly, the Schrödinger equation determines how wave functions evolve over time. A wave function behaves much like other waves, think water waves or waves on a string, because the Schrödinger equation is mathematically a type of wave equation. This explains the term wave function and ties into the concept of wave-particle duality. In quantum mechanics, wave function collapse, also known as the reduction of the state vector, occurs when a wave function, initially in a superposition of several eigenstates, reduces to a single eigenstate due to interaction with the external world. This interaction is termed an observation and is the essence of measurement in quantum mechanics, connecting the wave function with classical observables such as position and momentum. Imagine a quantum system existing in a superposition, a state where it can simultaneously be in multiple possible configurations. When an observation is made, this superposition collapses to a single state, an eigenstate. This collapse is one of the two processes by which quantum systems evolve, the other being the continuous evolution governed by the Schrödinger equation. But what triggers this collapse? When a quantum system interacts with its environment, the superpositions seem to reduce to mixtures of classical alternatives. However, the combined wave function of the system and its environment continues to follow the Schrödinger equation throughout this apparent collapse. It's important to note that decoherence alone doesn't fully explain the actual collapse into a single eigenstate. Historically, Werner Heisenberg was the first to employ the concept of wave function reduction to clarify the process of quantum measurement. However, when we perform a measurement, we only observe one definite outcome. This discrepancy is known as the measurement problem of quantum mechanics. To bridge this gap, the orthodox interpretation of quantum theory introduces the concept of wave function collapse and employs the Born rule to calculate the probable outcomes of measurements. Despite the undeniable success of these postulates in predicting experimental results, many scientists remain dissatisfied, seeking more comprehensive physical models. Rather than suspending the Schrödinger equation during the measurement process, some researchers propose that the measurement apparatus itself should be included and governed by the laws of quantum mechanics. Quantum theory, as it stands, offers no dynamical description of the collapse of the wave function. When viewed as a statistical theory, such a description is not expected. As Fuchs and Perez succinctly put it, collapse is something that happens in our description of the system, not to the system itself. Various interpretations of quantum mechanics attempt to provide a physical model for this collapse. These interpretations can be grouped into three main categories. The first group comprises hidden variable theories like the de Broglie-Bohm theory. In these models, random outcomes result from unknown values of hidden variables. Tests of Bell's theorem suggest that these hidden variables would need to be non-local. The second group models measurement as quantum entanglement between the quantum state and the measurement apparatus. This results in a simulation of classical statistics known as quantum decoherence. The many worlds interpretation and consistent histories models are part of this group. The third group posits an additional, yet undetected, physical basis for the randomness observed in quantum measurements. Objective collapse interpretations fall into this category. Quantum decoherence explains why a system interacting with an environment transitions from being a pure state, exhibiting superpositions, to a mixed state, an incoherent combination of classical alternatives. This transition is fundamentally reversible, as the combined state of system and environment is still pure, but for all practical purposes, irreversible in the same sense as in the second law of thermodynamics. The environment is a very large and complex quantum system, and it is not feasible to reverse their interaction. Decoherence is thus very important for explaining the classical limit of quantum mechanics. However, decoherence cannot explain wave function collapse. All classical alternatives are still present in the mixed state, and wave function collapse selects only one of them. In the context of quantum mechanics, function spaces often possess an algebraic structure, specifically a vector space structure with an inner product. This structure, combined with the topology on the set, forms the basis for much of the mathematical framework utilized in quantum theory. While the topology of these function spaces will be sparsely used in our discussion, it is essential for obtaining a precise definition of what it means for a subset of a function space to be closed. Ultimately, it will be concluded that the function space of wave functions is a Hilbert space. What does the wave function truly represent? Does it exist in reality, or is it merely a mathematical abstraction? These questions have puzzled some of the greatest minds in physics. Erwin Schrödinger, Albert Einstein, and Niels Bohr, to name a few, have all grappled with the enigmatic nature of the wave function. The Copenhagen interpretation suggests that the wave function represents probabilities and that physical systems do not have definite properties until measured. On the other hand, physicists view the wave function as a tool that reflects our knowledge about the system rather than an objective physical entity. According to this perspective, the wave function is a measure of the information in the mind of the observer. There are also those who argue for the objective reality of the wave function, believed that the wave function must have a tangible, physical existence. Einstein, always a proponent of realism. As we conclude our journey through the intricate world of quantum mechanics, with its mysterious wave functions and enigmatic interpretations, is not a closed chapter, but a continuously unfolding story.